Welcome to EDU World Space.
For this problem, on the topic of electric potential, we are told that electrostatic precipitators are used to remove pollutant particles from smoke. Now, the precipitators consist of a metal cylinder with a thin wire running along its axis in the center. We know that there's a strong electric field created in the middle of the cylinder directed inward. And we want to calculate the magnitude of the electric field midway between the wire and the cylinder, given the radius of the cylinder as well as the radius of the wire and the potential difference. We also want to calculate the magnitude of charge that an ash particle needs to have in order for a force to be exerted on it that is 10 times its weight. Now, firstly, we know from our text that the electric field within the cylinder E is equal to the potential difference VAB over the natural logarithm of B over A, and this is multiplied by 1 over R. Now here, A is the radius of the inner wire, or the inner cylinder, and B is the radius of the outer cylinder. So in this case, the actual cylinder. So we have an expression here for our electric field, and we can use this expression to calculate the electric field at any point R from the center. So if we look at part A, we want to look at the point that's midway between the wire and the cylinder wall. So in this case, the radius R is obviously A plus B over 2. And in this case, we are given these values. So that's 90 times 10 to the minus 6, or 90 micrometers, plus the radius of the cylinder, which is 0.14 meters. And so we get R to be 0.07004 meters. So we want to calculate the electric field at this point. And so we can go to our equation above and solve for E. So E is the potential difference between these 2 points, which we are given, times the natural log of B over A times 1 over R. And now all these values are known, so we can substitute them in. So this is a potential difference of 50 kilovolts, which is 50 times 10 to the 3 volts divided by the natural log of 0.14 meters. Let's suppress the units here, over 90 times 10 to the minus 6. And this is multiplied by R, which is 0.07004, and that's meters. So since all our values in SI units, we get an electric field strength of 9.71 times 10 to the power 4 volts per meter. So that's the electric field strength that we have at the center of the cylinder, so halfway between the cylinder and the wire. Now for part B, we want to take the electric force. We know the electric force F is equal to QE, and we want to set this equal to 10 times the weight of the particle. And from here, we can then solve for the charge required Q. So the force, the electric force, must equal to 10 times the weight of the particle, 10 mg. And we know the electric force is simply Q times E. So QE must equal to 10 mg. And if we rearrange this, we have that the charge required on the particle, Q, is equal to 10 mg over E. Now we know the mass of the particle, so we can calculate this charge. So this is 10 times the mass of the particle, which is 30 times 10 to the minus 9 kg, 30 nanokgs, times g, which is 9.8 meters per square second, divided by the electric field strength, which we calculated above, and that's 9.71 times 10 to the power 4 volts per meter. And so calculating, we get the required charge on the particle to be 3.03 times 10 to the minus 11 coulombs.